Hello and welcome to Chemistry 6. So, what we're going to talk about here is, remember in the last episode I started to speak about electron shells, and I noted that when we say n equals 1, this is the quantum number, and it refers to the 2 electrons in the first shell, and similarly if n equals 2, got 8 electrons in the second shell. So we're dealing with the quantum number, which has obviously got wide applications in other areas of science. So now what I want to do is I want to begin to think about ionization energies. Okay, so when an electron, when an atom loses an electron, it obviously becomes ionized. When an atom loses an electron, so this is all stuff that I've covered before. It becomes a positive ion. So now what I want to do is I want to focus on looking at how the electrons are lost and what the energy levels with respect to moles is, which is obviously the unit of weight, of mass. And yeah, don't want to confuse weight and mass, because obviously if you're in space that won't go too well. Alright, so when an atom loses an electron, it becomes a positive ion. So we covered that before. So it's is ionized. But of course, you don't just have to lose one electron. You can lose more than one electron. Okay, so let's do some definitions. Let's define what we're talking about now. Okay, so we refer to the first ionization energy of an element is the energy required to remove one electron, from each atom. So remember, like I said, well, actually I said this in electronics, and like I said, I don't want to cross them over, but at the same time, at this stage, they are similar. These electrons, they travel like a group. They're like in a pack. And from each atom in a mole of atoms, so you can imagine the mole is like the pack. And this ionization energy, it's sort of cascading its way through all the electrons, and removing one electron from each atom, going through the I always want to say cytoplasm. I could say phlogiston. Phlogiston, that's a good word. Okay, so it's a mole of atoms of an electron. Right, to move one electron from each atom in a mole of atoms of an electron. In the gaseous state. I haven't used this word before. So obviously there's different states of matter, with gas, liquid, and solid being the most common ones. In a gaseous state. Okay. And obviously it makes sense, because if you imagine, something like, like if you pack spheres or something, then when you have less packed spheres, there's a lot more freedom to move around, all this sort of stuff. Okay, so now let's do the symbols. So obviously chemistry involves a lot of symbolic manipulation, a bit like physics as well, actually. So you've got to get a handle on the symbolic notation. But then again, it's hard to say. a lot of these things are simply there because of tradition. So, and and these things are constantly being revised, and new ways of looking at these things. So, it's not necessarily that. Yeah, I've already used a few symbols myself, actually. But anyway, we're not gonna. I'm not gonna dwell too much on that. So we've got delta H. H. What's that? Delta H I1. Okay, so yeah, so that's the ionization energy, and we can say that what's a good way to put this? So this can be seen as basically saying how else can I put this? So yeah, so one thing that I should add then, actually, before we go into this, we'll go into this in a sec. That as we remove electrons, the cardinality of the name, so yeah, of the ionization methods, and I probably will think of other ways to put this, of the ionization energies, the cardinality increases. So essentially, what I wanted to put here is that the so you've got first, second, third, fourth ionization energies. Is known as a sequence of successive ionization energies. Okay, so there's obviously a sequence, and there's going to be many things that we're going to have to look at, of which I'm actually going to speak about for you today. I'm not going to go into the analysis today, but I am going to speak about what factors are going to affect these ionization energies. And obviously there are quite a few factors, as you can imagine. Of course, elemental identity, and we'll be speaking about that in a minute. So yeah, so we can imagine, if we go back to this, we can imagine this is the is the energy required to lose. So this is like the energy required to lose an electron. That's what that is. Okay. So now let's put it into actually into actual chemistry. So say we've got calcium here, and we're going to put the state there. We're going to put this a gas. And we're going to put an arrow. Now, interestingly, the arrow is different. But you know what? I'm not going to focus on that either. So we've got a positive ion here. Okay, positive ion plus the electron there. Okay, so you can see that this has lost an electron. So what we need to do is there's actually a table for this, and this table I'm going to also do in the next episode. But for now, what I'm going to do is just simply put that this energy, I'm going to write the same notation that I used above, and we're going to put a positive sign here, and we're going to put 590 kilojoules, and we're going to put mole, and then we have to the -1 is the notation. So yeah. So it does seem to reduce it by a factor. Maybe there's a historical reason for that. I may consider that. But either way, it's not changing the value much. So you're going to need quite a lot of power. You're going to need in the range of 490 kilojoules power to remove the first electron from an ionized calcium atom. So yeah. So the next thing to So I suppose I could put I1 here. I don't want to. I'm certainly not going to put it like that. I'll just put I1 there, just to indicate for now. I mean, obviously, you know, there are probably. I mean, there may be issues with the notation, but I'll just keep on trying to focus on improving those, and yeah, that's all I can really do. As long as I get the important information through, I think a lot of this stuff does tend to fall into place. It's just it's just how it is, really. Okay, so we're going to start now with the 1 plus calcium ion, and we're going to go to a 2 plus now. Okay, so yeah, so at this point you can almost sort of start thinking that you're making of doing analysis, but like I say, I do want to hold off on the analysis before exploring the actual reasons that affect these figures, because that way it's I don't know. I mean, I suppose analysis is generally done first, computer science, but it might not be appropriate for chemistry. So yeah, and then that's obviously what I'm going for here. We'll see. I'm hoping I've got the right way of doing it. So there we go. We can see that for the second electron to be removed, we need a lot more power, basically. I mean, what's that? That's almost double, really. Almost double. Not quite double. So a lot more power required to remove the second electron. Now, so obviously that's the second ionization energy, and the third and the fourth, like I've mentioned. So electrons can be removed till only the nucleus is left, and then of course you run into problems. So electrons can be removed until only the nucleus is left. Okay, and yeah, that's obviously beyond the scope here. So yeah. So now what I'm going to do, instead of talking about the actual figures and the analysis, that's going to come in the next video tomorrow. But what I'm going to do here is I'm going to talk about why. So why do ionization energies increase? What is the reasoning behind that? And then once I've explained this, I think it would be easier, yeah, to go into the figures. But yeah, I'm going to do some. Hopefully, I'm going to do some more sort of structural changes to the way things are here. I want to do more graphs, more good diagrams. All those things are things which are important for me to improve, I think. So why ionization energies increase? So as each electron is removed from an atom, so we're just sort of picking them off. The remaining ion becomes more positively charged. Okay, so you can imagine what that's going to do. It's going to make it. It's going to go further away. Yeah, I mean, that's how you sort of think about it. If you're thinking a number line or something, it's going to become more positively charged if you move the electron. So it's going to be a bigger sort of explosion to get the next one. Yeah, I can't think of any parallels, but I guess you can't always think of parallels. Because more positively charged. So yeah, so like I just mentioned, I'll very briefly write this. So moving the next electron away. From the increased positive charge. Requires a greater ionization energy. Okay. Okay, and now the final thing I want to say, which is perhaps so yeah, so when we look at the statistics, you know what? I'm going to leave this one for the statistics because I think I can just cause talk about large rises, and that's going to be good for the statistics, I think. So yeah, I'm going to leave this video here. Next time, of course, we're going to talk much more about ionization energies and the factors that influence them. But until then, thanks for watching.